The Foundations of Geometry by David Hilbert.
Chapter 7. Geometrical Constructions Based Upon the Axioms of Groups 1 through 5. Section 39. Criterion for the possibility of a geometrical construction by means of a straight edge and a transfer of segments. Suppose we have given a problem in geometrical construction which can be effected by means of a compass. We shall attempt to find a criterion which will enable us to decide, from the analytical nature of the problem and its solutions, whether or not the construction can be carried out by means of only a straight edge and a transfer of segments. Our investigation will lead us to the following proposition. Theorem 44. Suppose we have given a problem in geometrical construction which is of such a character that the analytical treatment of it enables us to determine uniquely the coordinates of the desired points from the coordinates of the given points by means of the rational operations and the extraction of the square root. Let n be the smallest number of square roots which suffice to calculate the coordinates of the points. Then, in order that the required construction shall be possible by the drawing of straight lines and laying off of segments, it is necessary and sufficient that the given geometrical problem shall have exactly 2 to the n real solutions for every position of the given points, that is to say, for all values of the arbitrary parameter expressed in terms of the coordinates of the given points. Proof. We shall demonstrate this proposition merely for the case where the coordinates of the given point are rational functions having rational coefficients of a single parameter p. It is at once evident that the proposition gives a necessary condition. In order to show that it is also sufficient, let us assume that it is fulfilled, and then, among the n square roots, consider that one which, in the calculation of the coordinates of the desired points, is first to be extracted. The expression under this radical is a rational function f1 of p, having rational coefficients of the parameter p. This rational function cannot have a negative value for any real value of the parameter p, for otherwise the problem must have imaginary solutions for which certain values of p, which is contrary to the given hypothesis. Hence, from Theorem 43, we conclude that f1 of p can be represented as a quotient of the sum of squares of integral rational functions. Moreover, the formulae the square root of the quantity a squared plus b squared plus c squared is equal to the square root of the quantity the square root of a squared plus b squared squared plus c squared. The square root of a squared plus b squared plus c squared plus d squared equal to the square root of the quantity the square root of a squared plus b squared plus c squared squared plus d squared. Show that, in general, the extraction of the square root of a sum of any number of squares may always be reduced to the repeated extraction of the square root of the sum of 2 squares. If now we combine the conclusion with the preceding results, it follows that the expression, the square root of f1 of p, can certainly be constructed by means of a straight edge and a transfer of segments. Among the n square roots, consider now the second one to be extracted in the process of calculating the coordinates of the required points. The expression under this radical is a rational function f2 of p and the square root of f1 of the parameter p and the square root first considered. This function f2 can never be negative for any real arbitrary value of the parameter p and for either sign of the square root of f1. For otherwise, among the 2 n solutions of our problem, there would exist for certain values of p also imaginary solutions, which is contrary to our hypothesis. It follows, therefore, that f2 must satisfy a quadratic equation of the form f2 squared minus phi sub 2 of p times f2 plus psi 1 of p equals 0, where phi 1 of p and psi 1 of p are necessarily such rational functions of p as have rational coefficients and for real values of p never become negative. From this equation, we have f2 is equal to f2 squared plus psi 1 of p divided by phi 1 of p. Now, according to Theorem 43, the functions phi1 of p and psi1 of p must again be quotient of the sums of squares of rational functions, and on the other hand, the expression f2 may be, from the above considerations, constructed by means of a straight edge and a transfer of segments. The expression found for f2 shows, therefore, that f2 is a quotient of the sum of squares of functions which may be constructed in the same way. Hence, the expression the square root of f2 can also be constructed by means of a straight edge and a transfer of segments. Just as with the expression f2, any other rational function, phi2 of p and the square root of f1 of p and the square root of f1 may be shown to be the quotient of two sums of squares of functions which may be constructed, provided this rational function phi2 possesses the property that, for real values of the parameter p and for either sign of the square root of f1, it never becomes negative. This remark permits us to extend the above method of reasoning in the following manner. Let f3 be a function of p, the square root of f1, and the square root of f2, be such an expression as depends in a rational manner upon the three arguments, p, the square root of f1, and the square root of f2, and of which, in the analytical calculation of the coordinates of the desired points, the square root is the third to be extracted. As before, it follows that f3 can never have negative values for real values of p and for either sign of the square root of f1 and of the square root of f2. This condition of affairs shows again that f3 must satisfy a quadratic equation of the form f3 squared minus phi2 of p and the square root of f1 times f3 minus psi2 of p and the square root of f1 is equal to 0, where phi2 and psi2 are such rational functions of p and the square root of f1 as never become negative for any real value of p and either sign of the square root of f1. But according to the preceding remark, the functions phi2 and psi2 are the quotients of two sums of squares of functions which may be constructed, and hence it follows that the expression f3 is equal to f3 squared plus psi2 of p and the square root of f1 divided by phi2 of p and the square root of f1 is likewise possible of construction by aid of a straight edge and a transfer of segments. The continuation of this method of reasoning leads to the demonstration of Theorem 44 for the case of a single parameter p. The truth of Theorem 44 for the general case depends upon whether or not Theorem 43 can be generalized in a similar manner to cover the case of two or more variables. As an example of the application of Theorem 44, we may consider the regular polygons which may be constructed by means of a compass. In this case, the arbitrary parameter p does not occur, and the expression to be constructed all represent algebraic numbers. We easily see that the criterion of Theorem 44 is fulfilled, and consequently, it follows that the above-mentioned regular polygons can be constructed by the drawing of straight lines and the laying off of segments. We might deduce this result also directly from the theory of the division of the circle, criterion. Concerning the other known problems of construction in the elementary geometry, we will here only mention that the problem of Malfatti may be constructed by means of a straight edge and a transfer of segments. This is, however, not the case with the contact problems of Apollonius.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.